Steve for the Southern California football team. We're very happy to announce our own visitor from Southern California, Louis Ho, who is visiting us from the Carnegie Observatories in Pasadena. Louis was born in China, had a vagabond lifestyle with spending his growing up in Mozambique, where he acquired the spelling to his name, and in the kind of rougher parts of Boston. And he then went to graduate school at Berkeley, where he did a thesis publishing the Palomar spectroscopic survey of nearby galaxies, which remains one of the cornerstones of studies of AGN 15 years later. And since that time, Louis has been, he did a postdoc at the CFA, Harvard-Smithsonian Center for Astrophysics in Boston, and then became a staff astronomer at the Carnegie Observatories. And he's, in addition to being a staff astronomer there, he is also consults and is a visiting professor at institutions in China and Taiwan. Louis is extremely prolific publisher and has published works in a wide range of fields relating to galaxy formation, and is one of the world's experts in black holes, which he's going to be talking about for us today. Thank you very much.
Well, it's a real pleasure for me to be here. It's my first time at University of Utah. The last time I was here was maybe 25 years ago. I was curious about the Mormon Tabernacle, and I managed to sneak in as a tourist, but I've never come back to the States since that time. Not because I was scared away. It's actually somehow I just never managed to. Anyway, I've had a very enjoyable visit so far, and I'm giving another seminar tomorrow on accretion physics at the astronomy department. You're welcome to join that. I've rarely given talks to non-astronomers. Okay, so I'm a little bit apprehensive about these interdisciplinary types of talks because we often speak different languages. So at the risk of insulting your intelligence, which is not my intention, I'm going to try to keep the technical details to a minimum and try to give you more the broad brush results and explain the broader implications without getting into too many technical details. The topic I want to cover is the influence of black holes on galaxy formation. Even if you're a condensed matter physicist, you may have heard that this has become an extremely hot topic in the last 10 years. And I'd like to give you a little bit of flavor as to why this is, what we have accomplished, and the remaining uncertainties that are yet to be resolved. In the last few years, there is some intersection between physics and astronomy, but usually at a very sort of abstract, large-scale level, like the cosmic microwave background. Perhaps you work on reionization. You think about the universe as just a soup of hydrogen, relatively simple. There are even some people who work on this. Okay, this is called it's the Dark Ages. Okay? This is not my own interest. This is fast forward roughly 14 billion years, and I am fascinated by how the universe has come to be, where stars have agglomerated into these giant complexes we call galaxies. And I'm particularly intrigued by why there is such a bewildering variety of galaxy shapes and morphologies and structures. Okay, some galaxies, these giant ellipticals, are relatively simple, homogeneous systems. Some are very, very fragile, low-density systems. These are disks. Okay, others have a bright component in the center that we call a bulge. Okay, which is generally older than the rest of the disk. Okay. Others have a central dense nucleus, which is identified here, which occasionally have massive black holes. Sometimes they don't, but occasionally they do. This is what the Milky Way galaxy might look like if you're able to step back at some distance and look back at our own home. A fairly run-of-the-mill galaxy with a bulge, and as I'll show you later, with a black hole. Deep images such as this, you might recognize this is the Hubble Deep Field taken by the Hubble Space Telescope, one of the deepest pictures that we have of the sky. It provides an amazing archaeological record of how galaxies evolved over the last 10 billion years or so. Okay? Some of these galaxies, if you zoom in, have familiar shapes that you can recognize in the local universe, but others have shapes that have no local counterparts. They have these sort of strange forms, almost as if they were embryonic in their early development. Because the universe was more compact back then, galaxies bumped into each other. They jostle with each other, and some of them collide and merge, and that does many things to transform the ultimate evolution of these stellar systems. This is what you would see as an optical astronomer with visible light. If you were to look at the same patch of the sky with an X-ray telescope, this is the picture that is recorded. I believe this is with the XMM Newton satellite. Okay? Every point here is a concentration of hard X-rays. And what they are is the high-energy radiation coming from accretion onto supermassive black holes that live in the centers of galaxies. Okay. This is a cartoon of what it might look like. We call these active galaxies. If they're extremely luminous, we historically call them quasars. Okay? But basically, these are the central regions of galaxies that we think contain a supermassive black hole with masses I'll describe in a moment, or maybe 10 to the 5 to up to 10 to the 10, maybe even higher, times the mass of the sun. Okay? They acquire their fuel by accretion of material from the interstellar medium of the galaxy, either secularly over time by transferring angular momentum internal to the galaxy, or externally triggering this kind of dissipation through gravitational torques that you could exert from tidal interactions with neighbors and merging galaxies and so forth. Okay. Collectively, the emission from supermassive black holes in the universe is energetically very important. This is a plot, essentially, of the energy density on the y-axis versus wavelength or energy, okay, or frequency, covering the cosmic microwave background to the infrared to visible, and this is the X-ray, the famous X-ray background. Okay. Over the years, it's been measured with better and better precision. This is a latest compilation of the X-ray background. Has a peak roughly at 30 keV. Okay, and again, this is a cumulative record of all of the high-energy radiation that's come from accretion into black holes. They even award Nobel Prizes for things like this. Okay, this was discovered in the 1960s by Giacconi, of course. The underlying sources that are responsible for this high-energy emission, again, are things we call active galaxies or quasars. Okay, so just to orient people, this is a typical spectrum. This is taken with the Sloan Digital Sky Survey of an object we call a quasar. And historically, ever since they were discovered in the early 1960s, people have immediately surmised that the ultimate source of energy has to be gravitational energy of material falling onto something very massive, something very compact, that for lack of a better word, is called a supermassive black hole. The arguments are very generic. Okay? There's a lot of luminosity coming from these things, something like 10 to the 12, 10 to the 13 times the luminosity of the sun. But it comes from a very, very tiny volume. We know this because this light varies like crazy. It fluctuates on all sorts of timescales. Okay, in some extreme cases, less than an hour on daily timescales, or months or years. Okay, but the fact that they vary so rapidly tells you this energy is coming from a very tiny volume. Okay, and if you look at these emission lines, which are gas that's photoionized by this underlying high-energy continuum, you will see many different metals, but if you look at the lines, you can see they have very large Doppler widths. Okay? If you interpret this as virial motions, it implies that whatever this material is, which is very close to the center, is moving around an object that's very massive. Okay? So out of this came the expectation for decades that there ought to be very massive black holes living in the centers of galaxies. They used to be very common early in the universe. They had their heyday sort of around redshifts of between 2 to 3. The earliest quasars we've found so far, as a record holder, is a little bit over redshift of 7, which I don't even have in this plot. Okay? But there are many quasars now known at redshift 5 and 6 and beyond from Sloan and other surveys. They sort of rapidly rise to this peak to around redshift 2 or 3, and then they dive like crazy. So that by redshift 0, where we are today, there are essentially no quasars. However, the black holes have to be there. Okay? So we expect that nearby massive galaxies ought to contain in their centers dormant massive black holes. And it's been the challenge of the last decade and a half to find observational evidence for their existence. And nowhere is the evidence firmer than in our Milky Way. Okay? I think many of you know these types of observations. These are proper motion measurements of the galactic center, the center of the Milky Way. This is the famous source in the center called Sagittarius star. And over a period of about 15 years, two groups, one from UCLA and one from Germany, have been tracking with adaptive optics the motions of a bunch of these stars over more than a decade. And enough so that some of them, in fact, you can track an entire orbit. Okay? And the conclusion is astounding. Okay? You can determine the mass very precisely. It's 4 times 10 to the 6 solar masses. Okay? So 4 million solar masses. But importantly, it has to be confined to this extremely tiny volume. Okay? The size scale here is about a light week. The implied mass density, that mass divided by that volume, is greater than 10 to the 12 solar masses per cubic parsec. At that kind of density, you can make plausible astrophysical arguments that basically it can't be anything but one source. Okay? You can imagine many hypothetical types of things you can throw in there, white dwarfs, neutron stars, things that are dark. But for various dynamical reasons, they really should not survive for any substantial amount of time. Okay, so this is, in astronomy at least, this is, as physicists, you may not be convinced until you see something on the event horizon or something, but this is pretty darn good. Okay, this is the best evidence that we have, and it's in our backyard. Beyond that, the evidence gets a little shakier, but it's qualitatively similar. Okay, so the next best piece of evidence comes from observations of what we call water megamasers. Okay, so these are masers. Okay, what Charlie Towns has taught us. Okay, they come from the water molecule at 22 gigahertz, and because of the conditions required for masing, they tend to be discovered in these sort of thin disk-like configurations. Okay, so there are only a few of these known. There are about a dozen to date. And you can use them because you can use radio techniques to measure the frequencies very, very accurately, and to trace the velocity, okay, as a function of distance from the center. And in this particular famous case of NGC 4258, you can trace this almost perfect Keplerian rotation curve. And the implied central mass is something like 40 million solar masses, about 10 times that of the Milky Way. There are now a handful of these things known. For the longest time, this was the only case known. Okay. Aside from that, most of the statistics really have come from the Hubble Space Telescope. And this was one of the reasons, in fact, that the Hubble Space Telescope was launched to begin with. Most of the work was done after they fixed the aberrated optics in the mid-90s. And this is one example of the observations we have taken. Okay? I've been fortunate to be involved in most of this work over the last 10 plus years. Okay, so what this is a giant elliptical galaxy in the Virgo cluster, Messier 84. Okay, there's a gas in the center, which is ionized by the nucleus. The line that we're looking at is H alpha. It's 6,563 angstroms. We put a slit across the center. Okay, HST has a resolution of about 0.1 arc seconds, a very fine resolution. We disperse the light, and we see this velocity signature. Okay, so this is blue shifted approaching gas, and this is red shifted receding gas. Okay, and from this we very simple-mindedly deduce what kind of mass is required to reproduce these velocities. More modern observations with a better spectrograph than that can actually map the entire velocity field around the nucleus, so you can actually produce more detailed velocity fields like this. Okay. In addition to using the gas as a tracer of the potential, you can, of course, use the stars. The stars are always there. The gas is sometimes there, sometimes not, and sometimes it's not stable. it could be perturbed, but you can try to use the stars, okay? And this has been done now basically more or less for 70 or 80 objects. And the bottom line is, we already knew this 10 years ago, is that every galaxy for which we did this experiment, and these were very expensive experiments because it's hard to get time in a Hubble Space Telescope, every time that we looked at a galaxy that had a bulge, remember that central round concentration of stars like these, we found dynamical evidence for a central dark mass. Okay. And that led immediately to the paradigm that quickly was adopted, that basically every bulge in essentially every nearby galaxy has a bulge, has a central black hole. Okay. That's result number one. Result number two is that if you plot the mass of that black hole versus the mass of that bulge, unexpectedly they lie on a very tight linear correlation. The more massive the bulge, the more massive the black hole. The Milky Way lies somewhere around here. That's a very large elliptical galaxy. Okay. This was published in 1998, and it elicited a lot of surprise, consternation, criticism, whatnot. Okay. 2 years later, we published a result that became even better known. Okay. This is the infamous so-called M-sigma relation. And what is being plotted here is the mass of the black hole. Okay, this is log in solar masses, so 10 to the 6, 7, 8, 9. Okay. As a function on the y-x-axis, this is the velocity dispersion of the stars in the bulge. The velocity dispersion is simply the random component of the velocity field. Okay, and this is measured on a fairly large scale. We call it the effective radius. It's basically the radius that has roughly half of the mass or half of the light of the bulge. On physical units, this is on a scale of a few kiloparsecs. Okay, so fairly large. And we find this distribution of points. Now, our initial publication in 2000 actually made the bold claim that all of the scatter that you see here is consistent with measurement error. Actually, that was the competing team. We said it was very small, but they actually said that the intrinsic scatter was consistent with 0. Maybe we're a bit too exuberant. We re-examined this a few years later, and it's not 0. It's more like 0.4 dex, which is still quite small if you think for a moment what we are saying here. Okay? What on earth does this have to do with that? The black hole is measured on scales of, the solar system, right? We talk about Schwarzschild radii. It doubles in mass and grows and accretes on a saltpeter timescale, which is, a few million years, 10 million years. This is the whole galaxy. This is kiloparsecs, okay? Tens of thousands of light years, okay? And the timescales involved here are tremendous. From giant ellipticals to spirals, they form over the entire history of the universe. Vastly different, vastly more complicated evolutionary history. What on earth are they doing lining up on a correlation that's, even if not almost perfect, still very tight? It doesn't make any sense, okay? This triggered an avalanche of speculations and papers. These two papers combined have about 5,000 citations. And some extremely smart people, maybe some in the room, have written very erudite post-dictions to try to explain this, because this is really was very unexpected. Okay? Whatever the explanation, the basic flavor of it is that somehow the black hole, even though it's on a very small scale, and I should have mentioned this, but the black hole, even though it's supermassive, it's really super dinky by galactic standards. The amount of mass in here is only 1/1000th of the mass of the galaxy. So in terms of gravitational influence, these stars know nothing about this. But somehow they have to communicate, this very small and very large scale. They have to somehow know about each other. Therefore was born the idea of feedback. Okay? There has to be some kind of energy feedback that regulates accretion and star formation. Okay? That regulates the growth of the galaxy and the growth of the black hole. The thinking goes that even though the black hole is very small in relative mass, okay, it releases energy with a very large binding energy, okay? Something times c squared, okay? And perhaps that is enough when it gets dumped into the galaxy to do magic to affect how stars form, how much gas remains, and so on and so forth. And the theoretical ideas have mostly been explored through numerical simulations such as this, okay, which are pretty high state-of-the-art smooth hydro SPH simulations. It envisions, of course, that the galaxy in the universe formed through hierarchical merging such as this. Two gas-rich galaxies come together. The gravitational torque of this interaction drives a lot of the interstellar medium to the centers of each of these galaxies, where it not only builds the black hole, but it also ignites very vigorous star formation. Finally, when these two galaxies coalesce, okay, that's when the real fireworks begin. A huge fraction of the gas in the galaxy gets funneled to the center on a very rapid time scale, where once again most of it gets formed into stars, okay, it creates what astronomers call a starburst. But importantly, a quasar is born. Okay, there's so much accretion onto the central black hole that effectively a galaxy explodes. Okay, so much energy is released that it obliterates, as you can see, the rest of the galaxy. It blows away all the rest of the gas and dust. Okay, it shuts off further star formation. It turns the galaxy so-called red and dead, and that's how you couple the very small and the very large. Okay, this is now become an extremely popular idea within the galaxy formation community, and it's become one of the sort of standard recipes for galaxy formation, as I'll explain more in a minute. Circumstantially, there is sort of some evidence to support this, okay, besides the M-sigma relation. If you look at the star formation history of the universe, okay, so what is plotted here is the star formation rate per unit volume, okay, so this is the star formation rate density, if you will, as a function of look-back time, okay, early times, present day. This is, in astronomy circles, this is called a Madal diagram, which says that out back to about a redshift of 2, stars used to form roughly at least an order of magnitude more vigorously than they do today. And there's been a precipitous decline in the rate of star formation towards low redshifts. What is overplotted here in this black line is the inferred accretion history of black holes derived from observations of quasars. And you can see that even though there is not an exact match at high redshifts, qualitatively the trend is, similar. Okay? And once again, this is said to implicate a connection between the very small and the very large. Okay? Somehow, the black hole accretion is affecting star formation and perhaps vice versa. A minority of these active galaxies are even more spectacular. We call them radio galaxies or radio loud AGNs. Okay? The scale of the galaxy that I showed you before would be enclosed, say, roughly within this area. What you see, in fact, are these enormous structures. Okay? They stretch out for hundreds of thousands of light years. Okay? This is roughly the scale of a megaparsec in astronomy lingo. Okay? There's a radio emission that comes from relativistic particles that are being squirted out of something in the center, presumably the black hole, okay, at relativistic speeds and emitting synchrotron radiation. Okay? These are so-called radio jets. And when they come out, they do tremendous damage to the environment. Okay? Typically, they're found in the galaxy clusters, which have what we call an intracluster medium, an ICM. Okay? And it's thought that this kind of energy deposition from black holes is very, very fundamental to the evolution, the detailed evolution of large-scale structures like galaxy clusters. And we see them in observations. Okay, this is an example of this is the galaxy in optical, shown here in color is a radio emission. Okay, and superposed with this radio emission, this blue stuff is X-ray gas. You can see it very dramatically. This is the case of Perseus in the Perseus cluster. You can actually see these giant cavities that are apparently being sculpted by the black hole in the center burping, once every so often. Okay, so there's a huge amount of energy that's being dumped into the environment, and supposedly this solves many, many problems that ails galaxy formation, including the so-called entropy floor in galaxy clusters. It solves the nagging age-old problem of cooling flows. Sorry, I'm getting a bit technical again. What cooling flows are, okay, so if you look at the galaxy clusters in X-rays, it's filled with this X-ray plasma. You calculate the cooling timescale of that X-ray plasma. It's quite short compared to the Hubble time. So you expect the hot gas to condense to a cooler phase and maybe eventually form stars. Astronomers have looked for this for 20, 30 years, and basically the embarrassing answer is that the gas doesn't seem to be cooling anywhere, even though you can back of the envelope calculate that it should be cooling. The magic panacea these days is that the reason it's not cooling all the way is because it's being reheated, because at the center of the cluster is this giant galaxy that has a black hole that's pouring out all this energy that's reheating the gas. Okay, that's a very, very popular resolution to this age-old problem. And in fact, it solves apparently a problem that's even more severe. Okay, so this is what I'm showing here is a mass function. It's a luminosity function, but you can think of it as a mass function. Okay, this is a space density of galaxies as a function of luminosity or mass, increasing that way. Basically, if you try to work out from first principles what is the distribution of galaxy luminosities or masses without incorporating AGN heating, you would get this dashed line. And this dashed line is nowhere close to the observations, which are the blue points. Okay? So if you include AGN heating, especially from these radio jets, apparently you can bring the predictions into much better agreement with observations, which otherwise is a total disaster. Okay, so this is just a very, very quick tour as to why this idea has become so popular, because it's a very powerful free parameter that theorists can invoke these days to solve all these problems in galaxy formation. That's why there are 5,000 citations to the original paper. That's very nice, but really troubling. As one of the people who published this, I feel compelled to tell these theorists that anytime you have 2 orders of magnitude more papers than you have data points, you should probably just step back, take a deep breath, and think about this a little harder. Okay? Why should we be worried? Well, for several reasons. If you look at this distribution of points, first of all, there are very few. Secondly, the distribution is very non-uniform. Okay? Most of the points are up here at the fairly massive end for fairly massive galaxies. This is a regime of spiral galaxies like the Milky Way. In fact, there are very few data points at all. Okay? So that's a concern. This is the Milky Way, by the way. Okay? So we just simply need more data to start. We have, until recently, no data up there. You see, the most massive black hole until very recently is only a few times 10 to the 9, a few billion times the mass of the sun, M87. If you look at the highest redshift quasars that I mentioned earlier, they actually could emit masses that are 10 times higher. They could be 10 billion, tens of billions of solar masses, just by their luminosity and energetics alone at highest redshift. But we have never seen them locally, so that's kind of troublesome. Okay? We also, until recently, have no data down here. You see that there's a cutoff in this plot. It's not because nature doesn't make black holes below here. It's hard to come up with a theory why there should be a gap between, say, 1 million solar masses and, say, 10 solar masses. Stars make 10 solar mass, a few solar mass black holes through normal stellar evolution, evolution of stellar, massive stars. Okay? Are there any objects below this threshold of 1 million solar masses? I'll show you in a minute that the answer is yes, but this has been relatively recent development. Beyond that, we really need to move beyond the local universe. This sample, which basically started off this whole business, is defined by black holes that are currently, finished. These are inactive black holes in nearby galaxies like our own, okay, where all the action has been done. Okay, this is the answer that we presented with. At which time back in the evolution of the universe did this correlation was first established? Okay, can we see this evolution, this correlation change with redshift as we step back in time? To do that, you have to go beyond the sample and beyond the local universe, and I'm going to show you a little bit of new results along those lines. Okay, you really have to go beyond this. I'm not going to give you too many details on the new observations, but I'm compelled to show you a few of the most exciting recent results. Okay, this was a paper from Nature last year by McConnell et al. And what is shown here, so most of these points is basically the same points that I just showed you before. It's just plotted with different symbols. There are two important developments here. One is that now there are 9 new mega-maser galaxies. These are the blue triangles that have been put on this plot. This is due to observations from the Green Bank Telescope in West Virginia. Okay, this is a paper by Jenny Green. This is extraordinarily important because these masses are actually very precisely measured because they come from these high-resolution radio observations. Previously, there was exactly one object, and now this sample has increased by an order of magnitude. Okay? The second thing is that there are now several reports of detections up here. And the record holder is NGC 4889. This is the brightest galaxy in the Coma cluster, okay, which has a mass of almost 20 billion solar masses. Okay, these are the green points of the new observations. This has been enabled by adaptive optics, laser-guided adaptive optics on 8 to 10 meter class telescopes. Okay, so very, very exciting. This is basically, we've broken a new barrier in terms of experimentation. And there are several things to notice that's different about this graph compared to the ones I showed you before. The first is that the slope of this infamous M-sigma relation is no longer 4. Okay? Literally hundreds of papers have been written to explain why the slope, was 4. I'm sorry, apparently it's more like 5. And if I were them, I wouldn't even write a paper about this because it's probably going to change very soon. Okay? So the fact is it's changing, so that's interesting. The second point is that, especially at low masses, the scatter is substantially larger. Okay? You can just see it. Okay? You don't have to do any formal analysis. The scatter is not very tight. And at the highest masses, there's a suggestion that, in fact, all the points sit above this line. Okay? So there may be curvature, there may be, who knows what. Okay? All right? So this is very interesting, but it's just stay tuned. I predict dramatic developments in the next 5 years or so. Okay, as the data come in. Okay, this is one result.
What's the difference between the red, the blue, and the black bits?
I think they're for different subsamples. Probably the red of the red points and the blue of the blue points.
Black all of them?
Presumably, yeah. I think that's it. Yeah. But again, I personally wouldn't take this as a final result anytime soon. Okay, because another very important development in the last few years is the ability to extend these mass measurements to high redshift. As I told you, that's really a key thing that we need to do if we try to understand how these correlations were established in the first place. And to do that, you have to resort to active galaxies, to those quasars, to those types of objects that I showed you before. But there we cannot measure the mass directly. There's just no way to spatially resolve anything on any small enough spatial scale to directly measure velocities, like we do for nearby galaxies. We have to resort to secondary approximations, okay? And it's very simple. This is the only equation I'm going to show, and everybody knows it, right? It's just the Virio equation, okay? So we can try to estimate the mass of the central object if we have two observables, namely a size scale and a velocity within that size scale. This is much harder than you think. Okay? How do we measure these things? Well, we can't resolve anything. Okay? Again, these AGNs are very far away. There's no telescope in any time soon that can possibly see this directly. The velocity part is easy. By picking quasars or so-called type 1 AGNs, these are the objects that, by definition, have these large velocity widths, which we interpret to be virial velocities, that these reflect motions due to gravity. Okay? So that part we can measure. The hardest part is to try to estimate the size. We cannot do it directly, so we do it indirectly. We use a technique that we call reverberation mapping. You can think of it as echo mapping. Okay? So AGNs and quasars, as I told you, they vary on different timescales. Okay? So unpredictable, irregular timescales. This is the continuum that fluctuates up and down. This is primary emission coming from the accretion disk. If you look at the emission lines, for example, H beta, it also fluctuates up and down. And in fact, if you look at the two curves, they're very, very similar to each other. That's because this is the emission that's reprocessing. This is the gas that's being photoionized by that continuum. But if you squint, or don't do that, do a cross-correlation analysis, you'll find that there's a lag. Okay? In this case, the lag is about a week. In the simplest interpretation, the size of this emitting region is 1 light week. Okay? You can do a little more sophisticated modeling, but that's the basic idea. Okay? This reverberation mapping. And this has been done for now maybe 40, 50 objects. It's very, very laborious. Every single point here is a spectrum that you have to take. You have to coordinate many, many observatories around the world, so on and so forth. Okay? Luckily, if you plot all of these lags, for a sample about, say, 40, 50 objects, nature is kind because this lag or this size happens to be correlated with the luminosity of the source. Okay? On average, the radius or the size scales as the square root of the luminosity. The more luminous the AGN, the larger the size. I don't know why. Most people, there are ideas of why, but let's just take it as a gift that nature has given us, that this is an empirical tool that we can use. It's very, very handy because now what it means is that all you need is a luminosity. You use this handy-dandy correlation, you can get the size, and from the spectrum you get the line width, and voila, you can estimate the virial mass. Modulo an uncertainty factor, this geometric fudge factor, because we really don't know what the exact geometry and the velocity field is, whether it's ordered rotation or it's random motions or probably some combination of the two. Okay? But we can calibrate it. And the way we calibrate it is that these blue points are those reverberation mapped objects for which we have a mass. But at the same time, because they're very nearby AGNs, we also have a measurement of the stellar velocity dispersion of the bulge. So we can put them on the M sigma relation. So the crucial assumption here is that active and inactive galaxies, okay, galaxies whose black hole happens to be on or off, are really no different macroscopically, and they should obey the same fundamental correlation. If you do that, you simply scale the points up and you can solve for this F factor. There are many caveats to that, but that's what we do because that's the only thing that we can do at the moment. If you do that, we can estimate masses of active galaxies with an accuracy of, say, factors of 2 to 3, essentially for all redshifts, because we can use the same technique for different emission lines. I show you that quasar spectrum. Instead of using optical lines for local redshifts, you can go to high-redshift quasar and use the ultraviolet lines redshifted to the optical band. Okay, so this is kind of the tool that people use. And in the last few years, astronomers now have, of course, quasars by the tens of thousands, 100,000 from these large-scale surveys like Sloan. And this has become a major cottage industry of people trying to estimate black hole masses for quasars at all redshifts. Okay, so here's one such exercise already some time ago, right? So as a function of redshift, this is black hole mass estimated in the way that I just described. And you can see that out to, say, redshifts of 4, these things are already 1 billion or more solar masses. They're already extremely massive. Until recently, this was the highest redshift quasar known in redshift 6.4, when the universe was only 0.7 gigayears old, 700 million years old. Okay, this is the spectrum shown in black. And the overlaid in red is the average spectrum of low redshift quasars. And there's an uncanny resemblance. You can just see superficially, they really look the same. What we found is that the mass of this black hole is already 3 billion solar masses. Even more astounding is the fact that we see all of these metals, okay, from carbon, silicon, magnesium, iron, when the universe was only less than a gigayear old. That's very interesting for other reasons. If you need to understand how it is that how these chemicals came about, because, for example, type 1a supernova should not have existed by that time. Okay, let me switch gears for the last 15 minutes and come back to this diagram that started the whole business and ask a related question. If you extrapolate this correlation to its logical limit, when there's no bulge, is it really true that there's no black hole? Okay, we said that every bulge has a black hole. What we didn't say, and we shouldn't have said, but we unfortunately might have misled people into believing in this NASA press release, is that when there's no black hole, there is no bulge. That is a different question, right? We looked at all galaxies that have bulges, and we found black holes. That's not the same as saying that every black hole has a bulge. Unfortunately, many papers and theories have been developed with that supposition that somehow, in order to make a black hole, you need to have a bulge. Okay, and I wanted for the last few years to test this, whether this is really true. This is extraordinarily hard, if not impossible to do, by direct dynamical measurements. We cannot use HST to find, rotation curves, close to these small galaxies with no bulges. We can do that for 1 or 2 galaxies in the very, very local, nearest to us. But because we need to probe scales generally to make these dynamical measurements, we need to probe scales that are what we call the gravitational sphere of influence of the black hole. It's the region where the potential is dominated by the black hole and not by the stuff around it, the other stars. Okay, and that's a very, very small scale. That scales with the mass. Okay, and even with the Hubble Space Telescope, you cannot do that basically beyond about a megaparsec or so. The only case that we've been able to do this successfully is the M33 galaxy, which is our local neighbor. Okay, and there we are quite certain that in the central region there is no black hole. Okay, this is a very, very rigorous limit of only 1,500 solar masses. But that's it. This is the only case that we can do this for now. Okay. Beyond the local group, we were able to do this for one more object, okay, this is M31, the giant Andromeda galaxy. And there, out here is a giant star cluster called G1. It's the most luminous, most massive globular cluster in Andromeda. Okay. We obtained very exquisite HST and Keck data, and we actually did find a compact object. The mass is kind of interesting. It's about 20,000 times the mass of the sun. Okay. People debate whether this is really a black hole with that mass. Perhaps this is just a cluster of stellar remnants, for example, neutron stars or white dwarfs or whatever. Okay. I'm not going to go into that debate, but this remains one of the best candidates for the lowest mass black hole that's been directly determined dynamically. But it's become very pressing. Okay, so this issue of what is the lowest mass black hole, what is the bottom of the mass function, has become more and more pressing as we learn more and more about the high redshift universe. Okay, because at some point we know that the universe was reionized. Okay, the current best estimates based on CMB polarization measurements suggest that the very first generation of stars that reionize the universe maybe happened around redshift 2017 or so, when the universe was 200 to 300 million years old. Okay, what were the seeds of the things that ultimately made these quasars that are already detected by redshift of 6? Well, some people speculate that this happens through so-called population 3 stars. These are almost metal-free stars. Because the metallicities are so low, the gas in the universe can't properly cool. It doesn't fragment. Therefore, you can make extremely massive objects, some of which may collapse directly into black holes with, say, masses of 100, maybe 1,000 solar masses. Okay, so these are types of simulations that Tom Abel, for example, works on. But from the standpoint of an observational astronomer like myself, this is all fine and dandy on the computer, but when are you ever going to observe this? Okay, so I cannot make practical progress by just thinking about these simulations. So for the last few years, I've been trying to think of a different observational strategy to at least put limits on this problem. And what I've done, along with one of my graduate students, Jenny Green, is to go back to the local universe. Okay, let's look at the Hubble sequence of galaxies. And let's concentrate on these galaxies. Okay? If small black holes exist in the universe, they probably are associated with the lowest mass, latest type, smallest galaxies. Can we find in these very late type, very low mass, low density galaxies any evidence that there is active nuclei going in the center? Is there any signs of accretion happening in the center of the galaxy? To the extent that accretion, this classic signatures that I showed you before, X-rays, broad lines, these classical active galaxy signatures, to the extent that that comes from accretion into a black hole, this would be a very cheap and very efficient way of finding such objects. Okay, so that's what we set out doing, is to try to survey for essentially mini quasars, tiny active galaxies in local tiny galaxies. I'm sorry, tiny AGNs in tiny galaxies. And historically, for the last, before we began this work, we knew of 2 such cases. This is very famous for people who know about the subject in astronomy. There are 2 examples, okay, POX 52 and NGC 4395. This may all look like gibberish to you, but the important point is that if you look at the spectral lines, they have the same characteristic, very, very broad, high velocity gas. It also has line ratios that indicate very high excitation, indicative of a hard ionizing radiation field. Okay, so these 2 cases have been known for quite a long time. What has also been known is how amazing these objects are. Okay, so this is 4395. This is the galaxy. And it's a very, very tiny galaxy. Okay, the AGN, or the tiny quasar, is in here. But this is an extremely low mass galaxy. It does not have a bulge of any type. It has a tiny star cluster, but it has no bulge. And the best estimates of the mass of the central black hole, based on a variety of techniques, is in this range. It's about 10 to the 4 to 10 to the 5 solar masses. This is the other object, POX 52. In many ways, it's even more remarkable. It's a tiny, tiny dwarf-looking thing. Okay, this is a very compact galaxy. And it, too, has a pretty low mass. Okay, this is below 1 million solar masses. In this case, about 10 to the 5 solar masses. But that's it. Okay, in the entire astronomical literature up until a few years ago, these were the only 2 cases known. So they were very rare. Okay, so we knew that to find many more of these things, we needed a very large survey. Okay, not hundreds of galaxies, but hundreds of thousands of galaxies. And this is where the Sloan Digital Sky Survey became extremely important, because that's exactly what it gave us. Hundreds of thousands of galaxies. Okay, good spectra. Okay, and what were we looking for? Once again, is this signature. Okay, emission lines with very broad velocities. Okay, that are qualitatively similar to quasars, but of course much, much lower in luminosity. And that's precisely what my student Jenny Green did. This is a mass function of black holes for all local active galaxies, about 9,000 here. And out of this sample of 9,000, we were able to find 200 sources that formerly had masses less than 10 to the 6 solar masses. So from 2, we went to 200. But to do this, she had to laboriously work through 600,000 spectra in the Sloan archive in a, shall we say, a very non-trivial way. Okay, this is not something you can download and do quickly. Okay, Anyway, so this basically has opened up an entire new field in the last few years. We've been following up these objects pretty aggressively, essentially with every telescope that we can get our hands on. These are Hubble Space Telescope images. We now have HST images of essentially all of them. And what I can say is that they do look like very small galaxies. Okay, you can see these are very late type, very low density spiral disks. Roughly 2/3 of them look like this, and roughly 1/3 look like this. Okay, without any trace of a disk or spiral structure, they're just very compact dwarf galaxies. So they're qualitatively similar to the two prototypes I just showed you, NGC 4395 and POX 52. But now we have a sample of a couple hundred. Okay. And by contrast, if I showed you similar HST images of classical quasars, the things with massive black holes, this is what they look like. Undeniably, they have a giant bulge in the center. Okay, so this is these are qualitatively different things. However, this is just 200 out of 600,000. Are they really that rare? We don't know, because the nature of the Sloan survey and the nature of these objects, because they are faint, is that we are very, very biased only towards black holes that are emitting near the Eddington limit. Because the masses are low, in order for them to make it into our detection limit, they have to be basically emitting at their maximum rate. Okay, so it's possible that these 200 out of 600,000 is just the absolute tip of the iceberg, but there's a much larger population of objects that are accreting at lower rates that we simply are not sensitive to. Okay, so using optical techniques and using something blunt like the Sloan survey, we can address that. We can, however, address that by going towards other wavelengths. So this is a complementary study using X-rays. This is data from the Chandra X-ray Observatory that has exquisite resolution and even more exquisite sensitivity. Okay. And what we found, this is a student of mine from Berkeley, is that in a sample of nearby late type, these low mass galaxies, 1/3 of them have these X-ray cores. Okay, so the red cross here is the photometric center of the galaxy, and the gray scale here is hard X-rays. 1/3 of these objects have hard X-ray emission. We don't think this is due to supernovae remnants or X-ray binaries or other stellar sources. Okay, we think that this is probably due to accretion from some kind of small, relatively low mass black hole, but that's accreting at a relatively low rate. So the space density, the fraction of these objects could be up to 1/3. In the future, we can directly try to prove this by actually getting the resolved stellar kinematics that we're after to be able to definitively say what the mass is. But that's going to have to wait for the next generation telescopes like the Giant Magellan Telescope. This is something that I'm very proud of because we're building at Carnegie. It's a 25-meter diameter optical telescope. Caltech is building a 30-meter version, and the Europeans are building something even bigger. Okay, but that's one of the key science goals of this large billion-dollar project is what we're going to do. Okay, so let me summarize what I've tried to convey. Okay, very quick tour. Supermassive black holes with masses of 1 million to 10 billion solar masses exist in all bulges that we've been able to survey. Over the last decade or more, we've established that the mass of this black hole correlates very tightly with the properties of the galaxy, specifically with the mass of the bulge or the velocity dispersion of the bulge. This has led to many ideas, but fundamentally to the idea that there should be a very close link between the growth of the black hole and the growth of the galaxy. And the whole concept of AGN feedback and AGN feedback regulating galaxy formation has arisen in the galaxy community. I've tried to give you hints that the scatter of these fundamental scaling relations may have been underestimated. And there may be complicated dependencies on mass and other things that we're just beginning to understand. This will rapidly evolve and change in the next few years. Okay? What I did not actually have time to discuss is how these things change with redshift. I'm sorry, it came from a different talk. What I did talk about is this point, okay, which is that over the last few years, for the first time, we've been able to empirically prove that the mass function of black holes does extend below 1 million solar masses. We've pushed it down to about 10,000 solar masses. Some people call these things intermediate mass black holes. Call it whatever you like. This is a new territory. What is important about these objects is that they exist in galaxies that do not have a bulge. Okay? Therefore, the formation of central black holes do not require the presence of a bulge. These are very, very good local analogs of the seeds, whatever the seeds were, that made the supermassive black holes that power quasars. And very importantly, because such low-mass black holes exist, and because galaxies merge, you will form, in many instances, highly unequal mass black hole pairs. You know, okay, 5 to 1, 10 to 1, 100 to 1. As galaxies merge, so will their black holes. Okay, and it's predicted that these highly unequal mass mergers will produce significant gravitational radiation that might be detectable with future experiments. For example, with LISA, which unfortunately won't fly, but if it were to fly, but certainly with, say, pulsar timing arrays and such things. Okay, so the gravity wave community is very interested in these objects because they precisely will produce the signal that they hope to one day detect. So let me just end it there, and thanks for your attention. Questions?